Each year on December 10th, thousands of worshippers convene in Scandinavia to commemorate the death of a man once known as the Merchant of Death. The scatological ritual features all the rites and incantations befitting a pharaoh's funeral. Haunting dirges play as the worshippers, bedecked in mandatory regalia, mourn the merchant. He is eerily present. His visage looms large over the congregants as they feast on exotic game, surrounded by fresh-cut flowers imported from the deceased Merchant of Death's mausoleum. The event culminates with the presentation of gilded graven images bearing his likeness. This ritual is, of course, the annual Nobel Prize award ceremonies, held every year not on the date of Alfred Nobel's birth, but on December 10th, the day he left this mortal coil. And today you're in for a treat, a conversation with a very alive Ray Weiss, who those of us who know him to be nothing if not incredibly interesting, provocative, mercurial, mischievous, and an all-around delight. I talked to him about so many things in this wide-ranging interview. It's really one of the highlights of my career, and it's fitting we did so on December 10th, which is today, the anniversary of the great Alfred Nobel's last breath on this planet. I heard some never-before discussed stories about some of the personalities behind the pursuit of gravitational waves, ranging back even to Einstein's day, but even closer to in time to people who sadly as well have passed away, including Joe Weber and Ron Drever, who are characters in my book as well, in losing the Nobel Prize, as well as in other accounts of the famous story of detection of gravitational waves from black holes in 2015 and 2016, and the announcement that reverberated around the planet, resulting in Nobel Prizes for three gentlemen, two of whom I have now had on the show, and the third one, Kip Thorne, I'm hoping to have on in the near future. You're going to hear Ray's advice for life, and he's a real live wire. He talks incessantly and persuasively about why it's important to do something you're curious about, even if it means that you change directions in your career every 5 years, reevaluating these fundamental questions that Ray will always ask himself. Even now, at age 88, he is still going strong. He is still sharp as a tack. What are those questions? Tune in and you'll find out. And you'll also find out about lessons that you can apply even if you're not a physicist looking for wispy imprints of the Big Bang in my case, or in Ray's case of collisions of massive stars billions of light years away from Earth. You'll learn about how to form a team of rivals, how to persist when those rivals seemingly turn their backs on you and maybe even on the whole project you agreed to go ahead with. You'll also learn about his upbringing and how different it was, and how you can get a little taste of the kind of curiosity that he had and instill that in either in yourself or also in your children or people that you are close to, young people that you're close to keep your projects, your science, your research, whatever you're doing, to keep it interesting and fun. And these are the key traits and takeaways you're going to learn on this episode. I had just such a spectacular time. Ray is a hero of mine, and I can't wait. You're going to hear about his new book that's coming out, written with Barry Barish, past guest on the Into the Impossible podcast, as well as Kip Thorne, who I do hope to get on the podcast. You'll hear some other Nobelists name dropped, but not for merely the sake of name dropping, but to really investigate what's wrong with the Nobel Prize and how is Ray personally going about trying to rectify the various ills that he perceives as existing within the current Nobel Prize structure. Nevertheless, he still believes it's crucially important, and it's hard to argue with him. I tried my best. I didn't succeed, but I hope you will enjoy going into the impossible with none other than the legendary Professor Ray Weiss. Enjoy.
Any sufficiently advanced technology is indistinguishable from magic.
But I do want to start, so I'll start now by welcoming everybody to this episode of the Into the Impossible podcast. I am your fearful host, Brian Keating, during these pandemic podcasts. Today, it's quite a treat to talk to a hero of mine, although he doesn't remember it. We've met a few times at MIT when I've had the honor of visiting there and speaking there, but I left my normal insignificant impression upon him, as I do on many people. But it's quite a thrill to have none other than Ray Weiss, a legend in his own time. Ray, welcome. Where are you joining us from today?
Well, I'm at home in Newton, but let me correct something that you said. I didn't remember, but now you tell me, yes, of course I remember.
Okay.
But we never worked together. That's and that to me is the thing that makes me really memorable. Memorable things, okay? Well, I know you gave a colloquium, but okay.
Right, yeah. You fell asleep after Alan Guth fell asleep.
No, I didn't know. Alan always falls asleep. I never fall asleep. I may not listen. That's something else.
Exactly. Well, Ray, you have been a mentor, and in many ways, I wish that I had worked with you or had the chance to work with you. And who knows? Maybe I'll help proofread your upcoming book.
Yeah.
But I want to introduce you. So, Ray Weiss, born September 1932, is an American physicist known for his contributions to gravitational physics and astrophysics. He's a professor emeritus at MIT. And so he's one of the leaders of the Ligo experiment, for which he received a share of the 2017 Nobel Prize in Physics. So, Ray, as you know, today is December 10th. Do you recall where you were 2 years ago on this date? Or 3 years ago?
The only reason why I think I might remember is because you asked. I think it has to do with Nobel Prize, because a lot of what you're thinking about. But I wouldn't have known that unless you had asked that.
And it's actually not. It is the typical day. Is the day that you received the Nobel Prize, of course, in Stockholm in 2017. But it's also the anniversary of the death of Alfred Nobel. I always find it interesting.
Oh, I did not know that. Okay.
Yeah, they give away the Nobel Prizes not on his birthday, as a sane society might do, but on the day of his death. It's kind of a scatological, as they say.
Well, what did he win a Nobel? I mean, what did he start? He started dynamite. Right?
That's
right.
So
you got to be careful with a guy like that.
Exactly. And actually, he started the prize. It's rumored, I talk about this in my book, that he started the prize out of some sense of guilt that he had for both the destructive power of dynamite, but also because his brother died. His older brother, Ludwig, died in 1888. And the Parisian newspaper that in the city that he was living in, Paris, printed a headline that said, "Alfred Nobel, the merchant of death, is dead." And they were kind of gleefully celebrating Alfred Nobel's death.
Yep.
And so this is like, Ebenezer Scrooge or, somebody, George Bailey finding out in It's a Wonderful Life how people are going to react. And so death plays a big role in the Nobel Prize. And in fact, I do want to talk to you about the death of your colleague, Ron Drever, who even Barry, I had a conversation with Barry Barish, your colleague and friend. And I want to talk to you first and foremost, what is the best aspect of winning a Nobel Prize and what's the worst? I've heard you describe it in German as, it's an additional thing in German, which I can't pronounce, but there's some word in German like Krankerwagen.
Noch dazu. I mean, but in addition, but no. Look, it's a complicated story, let me be dead honest with you. When I was younger, and I had never had much interest in the Nobel Prize. It was not something on my mind, and I even when it happened, I had double feelings about it. Okay, and I'll tell you what it is, and it's something that you may, because you are close to it too, have worried about, is that. How do you now, and I'm not saying anything profound that others haven't said, but it's got to be said. And that is in our day and age, when you're talking about people, you're a member of, I don't know how many people in your group, several hundred okay? I'm in a thing which has certainly from Caltech and MIT alone, 50 or so people, and then a collaboration which consists of another 1,000 or so. These are the people who actually, not that I didn't do something too, but this was a great big group of people. And it's sort of awkward to be pulled out of that group and given something which is actually a group effort. And I know that's part of the mystique of this thing. And it's part of the thing it's the hardest to really come to grips with. The thing is, how, when you now have a large scientific effort going on, and that's true whether you're doing cosmic background work or the B modes or the cosmic, any almost any large project nowadays, it was not thought about by the people, by if Nobel, if that's the person we have to blame or give the credit to. It's not the way we do science anymore. That is an individual who is the person who is responsible. In fact, I think that they must have a terrible time, especially the committees that look at this, to decide who, and they must do terrible investigations to find out, well, this guy did it and this guy did it, but he did a little more than I mean, I can imagine the arguments that go on in the Nobel Prize committee meetings. I've been on others, so I know the Gruber Prize, for example. I know exactly what goes on. And so it's very awkward then to be pulled out. And the only way I came to terms with it is to say, I can't change the way the world goes, but I can try to make myself into something which is halfway believable. Namely, I can be a symbol for the others.
Yes.
And that's the only way I can take that thing. Okay.
In all your talks, including your TED talk, you first and foremost always give credit to the team and say, basically, you're a stand-in cut out for the rest of the.
But it's true. It's true. It's not just the crazy modesty. It's true. And I understand why they can't do it. Now, I know the people who are trying to get around that, and I wish them luck, is the breakthrough people.
Yeah.
They're trying to do it with the whole team, and I'm very pleased that they can do that. But it does, and I had discussions with the people in the Nobel Committee when I was there about this. Not that, look, I'm sure everybody who part of a team has that kind of feeling.
Yeah, and actually, the Peace Prize is won by team. It was won by a team this year, the World Food Program.
Right.
1,000 people.
Well, yeah. So the thing is so that's a complicated thing. It's a complexity that comes with it for an experimenter. The good parts of it is, and I think the world needs certain symbols. And the symbols in this case are symbols that here is something that the society thinks is something that they relish. They think it's good, and they have given it as a thing, as a symbol to that science is something which the society badly wants and loves. Okay, and that piece of it is the part that we all share. So you don't want to screw it up by dumping on it. Okay. And that's one of the things that is very tricky about this. And the thing is, that part of it, being able to talk to people, especially high school kids, grade school kids, they're all over you because, of course, Nobel Prize is a big deal, But on top of that, I've done this for years, but even way before the Nobel Prize. I've been talking to kids in high schools and grade schools because I love to do it. But now it has a significance that they take a little more, let's say they're a little more serious about it. And and I hope I convince some people that they ought to go into science. I mean, that's worth something.
Yeah, absolutely. And I think, what's so striking to me, I asked two of your colleagues and friends, one, your colleague at MIT, Frank Wilczek, winner of the 2004 Nobel Prize. And I asked your friend Barry Barish, co-winner with you, I asked them, do you ever suffer from the imposter syndrome?
Oh, of course.
And only one of the two of them said yes. And I want to ask you, which one do you think said yes? And then do you suffer from the imposter syndrome?
I suffered for it right away. I can tell you where. I cannot guess between Frank and Barry. I don't want to challenge that one. You tell me, okay? Because I know them. I know Barry well, and I don't know Wilczek so well, okay? Mm-hmm. And Wilczek's a very bright man, and I love to listen to him talk. He's just full of ideas. And Barry is a superb physicist and an organizer par excellence. But so you tell me. But what the imposter thing was, I'll tell you, I think we all share that, well, most of us do, is that you go to this thing. And I remember looking at the king. See, I'll tell you a little bit. Maybe you know all the mores of this. There were three of us. That's in our case, okay? And the oldest one of us is the one who goes first. I don't know if you know that.
No, I didn't know that.
Yeah.
I knew that you went first, right?
You had to go for the oldest one went first. So that you were breaking all the ground. And my deepest worry was that when I got to the king who was standing there looking like he badly needed a smoke, he wasn't old and tottering, but he looked to me very uncomfortable. I said, and here is this heavy thing that is holding, and how are we going to make sure that neither of us drop the goddamn thing, okay? And so my worry was, let's make sure we don't screw up, either of us. And that was my biggest thinking as I was walking toward the guy. And then walking away from him, I said, this is ridiculous. I mean, look, where does how do I fit in the same group as Heisenberg or, you know, or Fermi or you name it? I mean, this is completely nonsense. And so that's where the imposter thing comes in. Okay.
Yeah. That's what Barry said too. Barry said he looked and he saw this little guy. He saw the signature of this guy in a book. I guess you have to sign this book.
That's right.
Take delivery of your and Barry said, no. I didn't. I couldn't take it. I got goosebumps thinking about, you know, Barry. We all have tremendous respect for Barry. And if this guy has imposter syndrome, what hope is there for me? And then I talked to Frank a day or two later, and I said, Frank, you discovered the phenomenon that would eventually lead to your Nobel Prize when you were 21 or 22. You didn't receive that Nobel Prize until you were 50 something years old, 31 years later in 2004. Was that excruciating for you? And how did you deal with it? And he had already said that he never felt the imposter syndrome. He kind of felt the anti-imposter syndrome, like he knew enough that he should know even more effectively, is Frank's take. And those of us who know him know that that's you know, he's sort of this wonderkind and just an amazing scientist in the grand tradition. But he said that it was excruciating to wait, you know, for 30 years plus to receive this, you know, this, I call it the golden engraven image. I have a piece of Hanukkah gelt here. Today is also Hanukkah. Yeah. So, you know, this one's about 10 years old from when I went to the gift shop there in Stockholm. But
what were you there for? Well, you were there for John Mather or what?
No, I didn't go to, I went to, there was a conference at the, at Nordita in Stockholm, and I couldn't resist stopping by. This is about 10 years ago, and kind of, you know, dreaming about it. But it's just so interesting to think, you know, everything that you've done, it seemed like, yeah, it's sort of this additional thing that is nice. You're not going to turn it down. It's interesting. No, people have turned down the Nobel Peace Prize, the Nobel Prize in Literature, but no one's ever turned down a physics prize. And I wonder why that is. I also wonder why, you know, with people like Einstein, you know, who was denied it for many years, as you probably know, because of him being Jewish and practicing what was considered non-Aryan science.
Well, that was part of it. No, Einstein got the award for one of his interesting stuff, but not the most important thing he'd done.
Yeah.
As you know, they couldn't settle on special relativity. They couldn't settle on general relativity. I mean, that was completely off the rock. I mean, you know, nobody had really proved that, oh my God, yes, that was just too modern. And, no, that was the problem. The Jewish stuff came later, I think. That's at least, I know a little because I've had, well, I mean, the people who really went after Einstein were Stark and Abraham. No, less Abraham, but mostly Stark.
And Leonard also.
And Leonard. Yeah. And they went, and Stark in particular was particularly unattractive about this.
Yes.
And I hate to think of it. My thesis as a PhD thesis was measuring the Stark effect. I can never get over it.
Well, I think, you know, Einstein, you know, basically provided the theoretical underpinning for the Leonard effect, you know, which is kind of ironic. Yeah. And that's why he won the Nobel Prize, or at least that was the citation, the photoelectric effect and Brownian motion and contributions, you know, kind of a grab bag. But I want to ask you, I've been doing a lot of interviews. I've interviewed people like Carl Wyman, and then Barry. But I've had the chance to interview people like Adam Rees, who's an observer, and other people that are more on the theoretical side, like Frank and Shelley Glashow, crosstown rival of yours in the Boston area. And I noted that, you know, when you hear about black holes and you hear about, you know, Einstein and wormholes, and Roger Penrose was on the show a couple of weeks ago too, and of course he just won the half share of the Nobel Prize in 2020. And I wonder, what do you think is the reason that
I missed it? We went dead for a second.
Oh, sorry. I want to know, why do you think that the Nobel Prize has recognized experimentalists and observers much more than theorists, and yet in the popular imagination, the theorists get a lot more attention? I mean, Kip Thorne, you know, is known for many things, but especially, you know, his work on Interstellar, and you look at Roger Penrose and even people like Stephen Hawking making these contributions as theorists for things that were never observed, like a singularity has never been observed directly. We've never, observed a wormhole, and people will talk about it as if they're as real as the actual detections that you make. So I guess, what is your take on the difference in prestige of a theoretical scientist versus an experimental scientist like you or me?
Well, that's a complicated question. I mean, I don't know enough of the history of the early Nobel Prizes, but most of the people who won Nobel Prizes in the early days, what I mean by that is before the revolution of quantum mechanics and so forth, were, well, they were, pretty pedestrian. I mean, some of those things. The guy who invented a particular way of making a lighthouse go around.
Yes, Dalin, Gustav Dalin.
Yeah, I don't know them all, but that eventually they got around to understanding what were the things that might be considered important by others. But the thing is that I think there is in the physics of Europe during the epoch of, and this I do know from people like Vicky Weisskopf, who had lived through this, and others who I know, in the early days of physics in Europe. And what I mean by that, let's say the time when the photo effect was discovered. And it was the experimenters that were considered the people who did everything. Mm-hmm. In other words, and theorists were considered something which was more mathematical. They were not really the scientists. And you look ahead and you'll see, you look back, it took a while for that group of people in Sweden to recognize theoretical work. In the United States, it was the other way around. I think the theorists were more, at least you probably know better than I because you've been studying this, but I think there was a higher acceptance of theorists much more quickly. And I have a funny feeling about why that might be the case. This is a surmise on my part. And that is that I'm not sure this is right, but I think it has to do in our case with people who made opinions. For example, I. Rabi, who certainly was forget about the Nobel Prize for a minute, was a central figure in American physics. Yeah. And when he was at Columbia, Columbia was the center of physics in the country. I mean, let's face it, in the 30s, the mid 30s and so forth. And he had I know him. I mean, I worked on stuff that he had worked on too. The guy who was my thesis advisor was one of his postdocs, and also later on very close friend of I. Rabi. So I got to meet Rabi in his manic ways, and he was wild, by the way. And on top of because he was extremely aggressive about certain things. And let's not go into all of that, but he was a very interesting person. And he began to realize that the work in this country was well divided between theory and experiment. See, a lot of stuff he was doing in the atomic beam business could not have been done without people like Schwinger who helped them out. People, other people who had been around understanding the quantum mechanics at a level which was complicated, let's face it, where you had to deal with, this wasn't just matrix mechanics, it was quite complicated to think it through. And then all these Clebsch-Gordon coefficients and all this mathematics, oh my God, they needed theorists. Okay, and so instead of being the handmaiden of the experimenters, they became individuals on their own. I think that happened faster in the United States than in Europe. Mm-hmm. That's just my guess. I mean, I don't know. I
think that does comport with the history, at least as far as I've referenced it. They actually would look down upon, people that did theoretical science in Europe, because real men did experimental science according to. And
I mean, later when I got into my age of being in physics, I resented the theorists because they represented what was important to do. And otherwise, I always said, screw it. I have ideas about this too. Right. And, my ideas, even though I can't formulate them as beautifully as you can, they're just as good. Yeah. And I want to work on things that I'm interested in. The hell with what you're telling me that's more important than something else. And I had the opposite thing. I didn't like the theorists getting in the way of everything. Okay. That's my own hang up. Okay. That's a different problem.
Right. I want to talk about that in terms of pedagogy and how things have really changed, even since I was a kid, 30, 40 years ago, between then and now. I used to be able to buy a chemistry set, and it had, ferric acid, and it had hydrochloric, it had all this stuff. Nowadays, I've got a bunch of kids and they're into chemistry. I buy them a set, and it's like, this warning, do not ingest the contents of this thing. And what are the contents? Is it, hydrofluoric acid? No, it's vinegar and baking soda and some chalk, and that's it. And I wonder, you go back to what your story, I wonder if you wouldn't mind recounting it, how you got, basically battled a raging inferno to get equipment to build phonographic record players, to build stereo hi-fi. What have we lost with the art of tinkering? I mean, nowadays my kids can't even work on a car. I mean, not that they're old enough to work on a car.
Well, neither can you. I mean,
I know that. That's what I'm saying.
Right. It's a goddamn computer that's killed that. But
so talk about, the pedagogy at the early age. You're an autodidact that learned about experimental radar from surplus kits and things that would kill you nowadays. So
now be careful with that. I think my own instinct is I know exactly what you're saying.
Yeah.
I mean, you used to be able to go to a drugstore and buy mercury. I don't know if you know that.
Yeah, that's true.
And many of us had pockets full of mercury. I mean, because it was fun to look at, and it
Quicksilver,
yeah, Quicksilver, of course. So anyway, no, it was a complete change. I think it has to do with lawyers. Mm-hmm. It has to do with the litigious aspect of our country. So I don't know if it's the same in Europe. I don't know. I don't know if it's the same in China or India. That's worth finding out. But most of the people that I know of who had experiments, and this is where it's different. Your kids, you buy a kit. That's because that's one way to do it. But many of the people who have gone into experimental physics, let's say a while ago, got most of their experience by being the fixer in the house, doing things. Like I'm not denigrating your children because they want to work on chemistry sets, but it's always very good to have, for example, a kid who works in a garage, again, works with people in a garage, or works with a plumber as an apprentice, or works with an electrician as an apprentice. And I think, and I recommend that over and over again. When high school kids say to me, what should I do to be able to do physics? I said, go rent yourself off to a guy and learn something.
Yeah.
You
develop
don't know
a trade. You had a trade at a 14-year-old. Yeah.
Exactly. And that then teaches you a couple of things. The most important thing is it teaches you how to problem solve. In other words, you watch, here's something that's screwed up, and you try this, you try that, and you begin to make a Venn diagram. You don't say it that way, but you say, yep, it's none of these things. So you stew about it. And so eventually you get it. So I don't know. I mean, for example, most of the people that were in my generation that went into physics did that kind of thing. I didn't remember having chemistry sets. That's the thing. Mm-hmm. I'm not saying you shouldn't have chemistry sets.
No. Yeah. I mean, I also I worked on a car as a 16-year-old because I couldn't afford to get it repaired, and that was a 1979 car.
Yeah, that was good for you. And you learned more from that than you could imagine.
That's right. Yeah. I always ask my students, they send me, I've gotten, all this Java coding, and I've gotten this differential geometry. I'm like, do you know how to weld? Like, tell me something cool, something interesting that you can do with your hands. And uniformly, I think they've gotten a distance from it. But I would be remiss if I didn't ask you to talk about those useful skills what drove you to do that, right? Because it's not normal, even for kids back then. I mean, they said Feynman used to fix radios in Queens by thinking about it. So he would hire himself out, and he was a theorist, and you were doing the same kind of thing, but with record players, what we used to call record players or phonographs. Talk about that and this neat kind of relationship between the microscopic vibrations of a tiny needle and then the reverberations of space-time. I mean, do you feel like there's any connection there? It seems too good to be true.
You're making it too dramatic. Okay.
Yeah. That's what I do.
There is a connection, and people have noticed this, which I didn't realize, but it's the noise. But that noise is the thing that kills you in one and kills you in the other two. I mean, if you're interested in music, you don't want noise. I mean, have you ever listened to a 78 record?
Of course.
You have? Okay,
I'm not that young. Yeah. Well, I listened to a 45 also.
45s and 33s have vinyl. They're different.
No, I know. Okay. The old ones had what, shellac or something.
Well, that's acetate. Right, exactly. So, and the shellac records were terrible. And you noticed it especially if you were interested in listening to slow, quiet music, like the second movement of a Beethoven sonata. Mm-hmm. It gets destroyed by that goddamn hiss. Okay, and so that was my big problem when I had to do things. No, look, I cannot tell you I don't have a nice story to say of an uncle or of my father or anybody like that. Why I got interested in electronics, I think it had to do with availability.
It was a puzzle. It seems like it was a puzzle. You love to solve these puzzles.
No, it had to do with the end of the Second World War. All things have to do with certain events that happened. And I remember I used to be a guy who loved to go to Cortlandt Street in New York. I don't know. You're not from New York, are you?
I am from New York, yeah.
Oh, good.
Yeah.
Cortlandt Street is down where the World Trade Center.
Right?
Well, no, it's north of the Battery, but it's pretty much near where the World Trade Center was.
Mm-hmm.
And you could go down to Cortlandt Street. This is during the war. You couldn't find much, but by 1944, 1945, when I was 13, 12, something like that, and I read popular mechanics and popular science a lot, and that kind of those magazines and they still exist, I think, but popular mechanics may not. But and in there you could make a relay that would make a rat trap that would close the door when you caught the rat. I mean, we had rat problems, so we had to build things like that. Okay, so anyway, the thing was that in my case it was simply that there was so much stuff coming back as salvage from the Second World War that I just saw it on the sidewalk, and I said, "What's this? What's that?" And I had friends who in those. Some of the people who ran those stores said, yeah, they told me, hey, we got a nice thing just came back from, South Pacific. You'll have to get the varnish off it if you want to do it. But we got a whole radar set there. You want the oscilloscope? And sure, I want the oscilloscope. How much is it worth? Oh, I don't know, a couple of bucks, something like that. I mean, that was a big deal, a couple of bucks. Okay.
Oh, yeah.
Okay. But anyway, so that's it. It was, I don't know, it was the availability. I'm telling you, I cannot give you a specific purpose. A specific source. Mm-hmm. The thing is that in my life, the thing that was important was music. Mm-hmm. And there was at that time in New York, and I won't go into this much more, but what was the fact that all of a sudden, I didn't have the discipline to learn how to play an instrument. That takes discipline. Later on in my life, I tried to do it and still doing it, but I never got any good. I'm not really good at it. But so I was interested in what you could pick up on, making electronics, because that was a lot easier than learning an instrument. And it was that was a lucky coincidence of three things that happened. And that's what started the whole thing. One was the junk on Cortlandt Street. Okay. The other one was that there was a movie theater in Brooklyn that had a fire behind the screen. And I was able to pick up these Altec Lansing loudspeakers by unscrewing them from the back of the screen. And the third thing was that FM radio was coming in. And FM radio already existed, but it had become commercial. And you could now pick up on FM radio, which is full dynamic range and 20 hertz to 20 kilohertz kind of sound. And you could listen to, the New York Philharmonic on the radio, and it sounded like you were right in the hall. And that I built several of those things with those speakers and all that stuff. And that started a business, which it was never intended. I mean, I would invite other immigrant parents. Europeans love music too. I mean, many of the Jewish families I came were interested in classical music and stuff like that. I had friends whose parents were, and they would come over and listen to this setup, and they would say, "God, this is fantastic. Can you build us one?" And I'll do it for parts. But eventually, I didn't realize how many people wanted that, and I got into real trouble. And then the phonograph record was the last piece of it. And that was an unsolved problem, insoluble problem. Because I tried, that's where the difference between what I call street electronics, which is what I knew, which, street electronics, all this sort of half-assed experience that some of it's right, some of it's wrong, but you have enough so you can get things done. But then with real certain mathematics applied to it, that's a different story. That's real engineering. And I didn't have that. So the challenge was, how do you get rid of that goddamn record hiss? And there were certain properties of it that you knew. It had high frequencies in it mostly, and it also always was there when the music was quiet. So could you make a thing that changed the bandwidth of the system as the music was loud and soft? That was an idea which sort of was quite obvious. Later on, people who really knew how to do that did it.
Right.
But I didn't know enough. And so all the cures that I could come up with were worse than the disease. Okay. So,
but it got you acquainted with solving.
Oh, yeah, got you doing it. Yeah. So I went to college for that. I went to college for that reason. I tried to solve that problem.
You actually, as I recall, you dropped out of, was it college or graduate school? I forgot. No, that was a different story. That has to do with being sort of a kid and being adolescent. No, I ran into a wonderful girl who was a spectacular pianist. And I just couldn't live without her.
And but she could live without me, and that was the problem.
And that eventually brought you to Princeton, right?
Yeah,
And,
no, that took me to Chicago, where she was
Chicago.
a student,
Ah,
and
okay.
then I flunked out. And then the transformation, and this, if you're interested in the transformation, that transformation took place after I flunked out. This was in the middle of the junior year at MIT, and I walked all around an old building at MIT called Building 20, which is where the radar was developed. And I found a lab which looked to me like they could use an electronics technician, and it turned out they could. And I became a union member. I dropped out of school completely and became a card-carrying union member, and became electronics technician for a couple of years in a lab of Gerald Zacharias's. And he is the guy who saved me in every way possible. And the thing he was working on in the end was atomic clocks. And he put me into the bug of Einstein. The experiment he proposed to me was, after we got to know each other well, since I was expendable, I was not a student, there was no responsibility. There was no PhD to give, nothing like that. So he said, I want to do an experiment, he said to me, where you and I, and maybe somebody else, we build some new clocks, which are better than the ones we have. And we'll do this experiment in Switzerland. You with your new clock will be on top of the Jungfrau, and he will be down in the valley and in the Jungfrau Valley. And we will send signals to each other from these atomic clocks and measure the Einstein redshift. That was the big experiment we were going to do. And what happened is that this fancy clock that he had invented to do this didn't work. Mm-hmm. And that's a long story. I don't think I want to go into it. But
I do want to. I have heard you describe that the cesium fountain or beams and so forth. Yeah. I don't want to talk about that specifically, but I want to talk about a general question in the philosophy, which I don't think gets talked about as much. I know you're not like huge into philosophy, but the philosophy of experimental science. And this question is as follows: how do you know when to shut off an experiment? We can always turn on an experiment, keep it going. If you keep shoveling in more money in the NSF, which we'll get into, keeps approving your funds, and you have graduate students and they don't abandon you. But when do you shut it off? How do you acquire that wisdom or judgment? Because I think that applies to things outside of science as well.
Well, I have several examples of that because I failed in a few places. My first failure was making a better clock. Okay, that was not. I was a technician at the time, but still. And what happened is Gerald is the one who gave up. Gerald, he had very big fish to fry. For example, and this was all in 1956. I mean, before most people that I know were born. Okay, and what happened? He got the idea that American secondary and primary education in science and mathematics was really screwed up, and he was right. So in 1956, he got an idea of how to fix that. And you're probably a beneficiary of that. Yeah. I don't know. It was called the Physical Sciences Study Committee. Right. And they did a beautiful job, write a really modern textbook and so forth, among other things. They also so he decided that he was going to quit that experiment. It was for him was he had more important things to do. Right. Well, what did I have to do? I want to find out why the goddamn thing didn't work, right? Mm-hmm. And so I didn't cost anything. The thing was there. And so we found out what was wrong. I mean, it took a couple of months to do that. And in fact, there's a flaw in the way we teach statistical mechanics. I don't know. I might as well tell you right off. Yeah. It's but the idea of this clock was that the big idea of getting a better clock was always to get more observation time for looking at the atomic system. The longer you could do that, the smaller the uncertainty in the frequency. Okay, that was the basic idea. And so what you do, you use higher frequencies. That was the other way of doing it. But you were stuck here with cesium, 10 gigahertz. Okay, so the idea was how do you get in an ordinary apparatus, a small atomic clock that takes a millisecond? You have about a millisecond to watch the atom. And he said, well, can't we get up to about a second to do this? Okay, that would give you a factor of 1,000. And his idea was to throw them up like baseballs.
Like a fountain, yeah.
Make a fountain. Well, what did I know?
Which is used today, yeah.
Well, of course, it works beautifully today. It's called the Zacharias fountain.
Yeah.
But it didn't work in those days for a very simple reason. You're dealing with a tiny part of the fraction of the Boltzmann distribution in the beam. 1/20th, maybe 1/30th. And the fast guys are coming back and they're hitting you in the tuchus. Okay, so here's this beam going up and trying to come down again. And the fast atoms, there are many, many of them. And what they eventually do is throw all the slow ones out of the beam.
Interesting.
That was the problem.
Ah.
And if you start, and I was able to prove that by measuring the time of flight at different heights in this apparatus. But the apparatus grew to be 33 floors high, but we never didn't want to give up. We kept looking for faster atoms. No, none of them worked. And so consequently, what happened is that nowadays, as you point out, you can take and make that's how some of these clocks work. You can take a standard clock now, let's say on the sodium, any of the optical clocks, and lift it up by a centimeter. Lift it up by a centimeter, and you can measure the redshift.
Yeah.
It's really amazing.
But in 1957, you couldn't, right?
Mossbauer
effect.
No, Mossbauer. Well, that's how Pound eventually did it.
Yeah.
And that the whole thing became less interesting. But it was that business of learning learning about Einstein and how he thought. I fell in love with the guy. I mean, that was fundamentally the end of it.
He's had he had a reputation for some blunders.
Of course, I know them all. That's not the point.
Do you know what his most cited paper is, Ray?
I don't know which it is.
It's the EPR paradox paper.
Oh, that's a shitty paper. I'm sorry.
I know that. No, I know that.
I know it shouldn't be. It's a crappy paper. It's a bad idea. I hate that paper. And I think it's Podolsky's way of staying a citizen, or staying in the United States. It was all that very complicated thing where he was trying to help all these immigrants who he had assembled around him. And if he hadn't been the first author of that paper, nobody would have read it. I think that's the trouble.
Yeah. And it really was, I think they had animus towards he had resentment at least towards Podolsky ever after. But getting back to the experimental, kind of shutting down. So as you know, from being one of the pioneers in the field of cosmic microwave background radiation research, I always point out, Kobe could have detected, the polarization of the microwave background if you kept it running for like 100 years or something like that, just to make an extreme case. In other words, we win, but we win very slowly with time. We only win as the square root of time. So to get twice as good, you need 4 times as much time. So I want to ask you, when you make a decision to end a life, is it like, like killing your pet worm, or is it like, unplugging a computer? What does it feel like to end an experiment that's successful? Yeah,
but let me say, it's always something a little different than what you think. I mean, if we take that, it's a good example. You could have run Kobe for a long time, except you wouldn't have been able to. Liquid helium wouldn't last. That's a real problem. Okay,
that's right. Yeah.
And on top of that, where they were detectors you wouldn't even think of using anymore. I mean, they were so crude. Yeah. The bolometers with 10 to the minus 15 NEP or something like that. Yeah, you wouldn't even touch them anymore. It's ridiculous. So it turns out generally you give up on. Generally when I gave up on experiments, it's either one of where you want to know what went wrong because there was something wrong, and I learned something out of that. Okay, I learned that the Maxwell distribution doesn't work. Okay, in a beam. That's a piece of knowledge that you ought to tell people about. Okay, that's a result. Okay. On the other hand, most of the time it is that you've worked on it. It hasn't worked. You do the noise analysis and you've convinced yourself that you need another 2 orders of magnitude or something like that. Where you finally understand the experiment now, and then you say, I can't do that. That's just too big a jump. And then somewhere later in your life, you suddenly find out, oh my God, here's this piece of technology that solves that problem that I worked on that didn't work before. And sometimes that is very useful. And by the way, that's remarkably what happened in Ligo a lot. In Ligo, for example, the fact that none of us gave much attention to squeezed light, for example.
Yeah.
Okay. And then all of a sudden it turns out that, oh my God, we can use this, and,
that was Brzezinski, right? Brzezinski that was his calling card for many years.
Be careful with that one. You're right, but not quite right.
Okay.
What it was is that Brzezinski saw right away that a mechanical bar would be troubled by the quantum limit. In other words, that the thing that senses the bar is going to put enough noise into it, the quantum noise into it, so that it'll mask the signal. And then he tried, and he didn't come up with a very good way of doing that first. He kept thinking about something he called quantum non-demolition detector systems. And these are all second order things. These are still, I don't think they've paid off yet, but they will. They will. It's the idea that I don't know, the closest thing to it is, it's funny that people now talk about measuring weak measurements. Do you know what I'm talking about? Where you don't actually force the system into an eigenstate.
Right. It's a second order kind of perturbation theory. Right?
Yeah, exactly. And that is what he was actually, I think, pushing. And the guy who actually is responsible for the squeezing and its application is Carlton Caves. I don't know if you know of him. He was probably at Caltech when you were at Caltech. He was a student of Kip Thorne's. And Kip, by the way, this is something you probably don't know about Kip. Kip has a very what I will call tactile sense about physics. It's not. He's a theorist, yes, and he doesn't make mistakes when he makes equations like I do, but he thinks that he does it right. But he also has a wonderful feeling in his gut about the physics. And let me say what he did. Kip did two things. He convinced Carlton that there was something wrong with the way we thought about where the noise comes into the interferometer. I don't know. It's a long story. I don't think I want to tell it unless you want it. But the important thing is that the Carlton's discovery was that the noise, which we had always thought was shot noise and momentum noise, which is the other two noises that come in a photon system, that those were independent in a way of each other, and they're not. And it turns out they come in not where you think it is. They come in where the detector is. They are fluctuations in the vacuum field, and that vacuum fluctuation distributes itself in the interferometer in such a way that if you could somehow reduce the vacuum fluctuations coming in the dark part of the interferometer, you could win, and that is squeezing.
Okay. So it wasn't the kind of complementarity that Brzezinski. Yeah, he had
it was very different.
Very different. Yeah, actually, I didn't appreciate that until just now.
And what it is, and then just one step further, so you'll have a little bit. It's very easy to see it. What you require is paired photons. What you want to do is prepare photons at the dark port so that they either have, as a pair, they have amplitude sidebands or phase modulation sidebands. And those are the two variables that are the quantum canonical variables.
Conjugates,
The conjugates, okay? And so consequently, you can adjust that. Whether you make the two pair of photons, you see the way it does, you have a medium with gain, in comes the vacuum fluctuation. The vacuum fluctuation causes an induced emission in that medium. That's a spontaneous emission, if you want to call it that. And you can tailor that so that another photon comes along with it. So there are two photons. And those photons can either be noisy in amplitude or noisy in phase. And in different frequency regimes of the gravitational wave detector, you use one way or the other way. And that was an invention that was made by Carlton Caves.
Interesting.
Among other things, yeah.
So on that front, there's, as you know, there's a lot of lore about LIGO. It's a wonderful story. It's a tale of many, hundreds of millions, if not $1 billion. It's a tale of.
It is $1 billion. It's running. It's $50 million a year to run it.
Yeah, exactly. Everybody always says, "Oh, this new collider will cost $20 billion," and I'm like, "Yeah, and $500 million a year to run it." But I say, when Jan Levin, who's a friend of mine, she's been on the show multiple times, and she wrote a beautiful book about it, which you're a major character in.
Yeah, I know the book.
and I know you guys have had conversations, but it's a wonderful story, and part of the story is the suspense. Like, will they detect it or won't they detect it? And I want to pose kind of a little bit of a provocative question to you. When you set out to measure this, you had Einstein. Again, we're going to keep talking about your friend Albert over here. You had Einstein, the genius, who'd most of his predictions panned out in one form or another, except, even his blunder was a blunder, because we now later found out dark energy was a necessity to include in our cosmological model. Yep. But when I try to measure with my colleagues on the Simons Observatory or BICEP, we try to measure inflationary gravitational waves. We don't have like Hulse and Taylor, standing in the background saying, "Hey, thank us, guys. We measured that gravitational waves are real." Yes, we didn't directly detect them, but was it really such a surprise? Tell me the honest truth. Did you really doubt that you would ever make a detection of gravitational waves or that they existed?
Well, okay. Well, you've entered the realm of science history there.
Yes.
The book that tries to explain a little of that is Kennefic's book. Do you know Daniel Kennefic?
I know. I haven't read that book. I've read Harry Collins' book, but
the hell with Collins' books. And take a look at Daniel Kennefic, who is careful. He's a physicist.
Yeah.
And he has written a beautiful history of just what you asked about.
Okay. And
it goes way back. It goes back to 1916. I don't know if you know that.
No. Oh, that was right after the general theory.
Yes. And the very first thing that I'll tell you now, just to whet your appetite.
Yeah.
It turns out 1915 is, of course, the full theory comes out. Okay, in 1916 he writes a paper on the perturbation theories that you can use, so you don't have to solve the metric exactly. Okay, and he picks a couple of examples, the Perihelion advance again, and he shows that there's Newtonian limit, and he introduces gravitational waves for the first time. And he does everything right. He gets the kinematics right. And he takes a big guess that they travel at the velocity of light, which we now know to an exquisite precision. But then he completely screws up the relationship between the source and the field. Okay?
The two sides of the equation.
In other words,
G and the T.
no, he finds that a system that there's an equation you'll find right in the sort of near the end of the paper. You have to read a little German, but now it's translated. You don't have to read German.
Yeah.
So anyway, well, you'll find out that all the terms in the are terms that have to do with the second derivatives of the moment of inertia of a system. And it turns out the signs for all the terms are positive. Those make it. So that says a thing that's spherically symmetric, that expands uniformly and that contracts uniformly, will radiate. That's a no-no. Okay? It goes back even before his. Okay. So it turns out, but in that paper, at the very end of the paper, he starts doing a little bit of a dimensional analysis, even though he had the thing wrong. But the numbers are still not wrong. In other words, the orders of magnitudes of the strains, the metric terms, they're still about right. It's just for the wrong motions, okay? Because it has much of it right. And it turns out he makes one very, very simple statement at the end. He says, here is an equation, the equation he writes down. And it says, you know, this thing we have just been talking about in this paper will never have any influence in physics.
Yes.
It's much too small to even be contemplated.
He said that about gravitational lensing too.
No, he said that about gravitational waves.
Yeah, okay. I know. He said it about both, and both have been detected. Yeah.
Well, yeah, but this one, I've given talks trying to invent what Albert was thinking about, you know, and indeed, if you look what he knew at his time, it was impossible. You're talking about strains of 10 to the minus 42. Okay, I mean that's for a train smashing into another train in the radiation zone makes a strain of 10 to the minus 42. I mean, that's the biggest thing you can think of that you can make. That's unmeasurable. And then he looks at binary systems and sees that binary stars, with a period of a year, you know, they'll do what Taylor holes have, but he recognizes they should fall toward each other. But at the rate they fall toward each other is so small that you have to wait something like 10 to the 12 years, 10 to the 13 years to see it. You can't, the telescope, you'd never see it. So anyway, he comes to that conclusion. And so then in 1918, he writes another paper, which is solely about gravitational waves. And he gets right now the relationship between the dynamics at the source and the field. But he doesn't say anything about the believability of seeing it. Okay, so good old Kennefic will tell you about that. But then he'll take it to 1936, where he really gets himself into trouble, again, with one of the immigrants. Okay? This is a paper where he is with, I'll forget the name of I'm sorry, I can't dredge it up right away. It's the paper he and X, whose name I'm trying to remember, submit to the physical review. They solved to see if there is a solution of the Einstein equations, which is purely radiative. In other words, you know, that you have a really rigorous solution that is source free in effect, and can it propagate as a radio? And they prove that it can't be done. This physical review gets this. Do you know about this?
Yeah. I mean, I vaguely, but I don't think the audience will know about it. So it's worth continuing.
Well, so at any rate, and so what happens is they publish it. A guy named Robertson, the metric, you know, who was at Princeton, Richard Robertson, I think it is. I don't remember. Gets it to the review. And it takes a while for the review to take place. Einstein gets miffed about that. It hasn't been published yet. He calls the physical review. What's going on with this paper by X and Einstein? And he gets told that, well, they send the things out for review, and he gets pissed off at that. And I don't know if you know that. That was legitimate. In Germany, they don't do that. Right. And so, okay, and then Robertson's review gets there, and Einstein sees what he did wrong, and they then, in chagrin, sort of effectively submit it to the Franklin Institute Journal. Okay, so mistakes are all over the place.
Right.
At any rate, the final mistake, and the one that we had to live with, and that's why were specifically worried. And I don't know if Barry told you this, or Kip will certainly tell you this. I'll tell you, is that it was the disaster associated with Weber.
Mm-hmm. Yeah, I was just going to get to Weber, but yeah, please go on. Yeah.
I mean, I knew Weber pretty well because during Kobe, I would go visit him a lot. You know, he was right there next to Goddard, so I went. I mean,
yeah, he's sort of a pitiful, pathetic character in some ways, but he was a great scientist, right?
He's a very good scientist. I mean, some people will reject what I just said, but. And I'll tell you what the trouble is. He didn't have enough the ability to be self-critical. That's, I think, the fundamental trap that he fell into.
Would you say that's like confirmation bias? Like he saw what he wanted to see and discarded?
Well, I can't prove you that. That I can't do. But I can tell you what I know for a fact.
Yeah, please.
And that is that I would visit him. By the time he had published, I mean, it really became. He published in '69 that he had detected gravitational waves.
Right.
And I started going to Goddard a lot for Kobe in 1972. Okay.
Really? Kobe started that early?
Yeah. Well, John Mather invented Kobe and as a graduate student.
Oh, okay. Oh, the FTS and everything. Oh, I didn't know that.
Have you ever had John on your little program?
No, I know John, but I haven't had him on. I'm going to have him on.
Oh, boy, you'll be fascinated.
Yeah, I will.
Okay.
That's a great idea.
And so what happened is that I started realizing that Weber was a lot of people. I mean, Weber's thing went on. A lot of people didn't see anything. That caused a great deal of problems. And for example, there were physical society meetings where a guy like Richard Garwin, who was a very good scientist at IBM and Columbia, had built a little bar much more technically sophisticated than the one that Weber had built. And he knew exactly how sensitive it was. He knew everything in the noise about it. And he said he didn't see anything. And Weber's only defense was, you didn't do it my way. And that's not a defense, you see. And
but do you think, Ray, that he might have felt burned from the experience that he had with Towns and the Maser?
No, he didn't know. That was he felt, I don't know about that one. That was the place where he didn't vote with his feet. You understand?
How do you mean? How do you mean?
What I mean by that is he wrote a paper on negative temperatures in a IEEE an IRE journal. Okay,
mm-hmm.
Towns had written it in a physics business and actually was working on it. Mm-hmm. And a lot of people in microwave spectroscopy were trying to figure out what to do next, and it didn't look particularly attractive to him. At least he wasn't going to do an experiment to look for negative temperatures, but he wrote the paper. And so he, as I say, didn't vote with his feet. He didn't actually go out and do the experiment. And the experiment was done by Towns and others with ammonia, you know. And so, but yes, that was a sad story. But the important part is that here he invented a lot of things which we now use for the gravitational wave thing. He invented the idea that you want to look for a strain. He had it differently than we have it. He was looking for tidal force, but that's just a way of writing it. We look for an actual change in the geometry. It's the same story, just another way of talking about it. And and then he had the idea that there would be a non-Gaussian character to the noise, and he had to have coincidence experiments. And we do the same thing.
Yeah.
And but he had the idea that, and it was the people who worked with him at that time was John Wheeler. Mm-hmm. Wheeler actually suggested to him to look into how one might detect gravitational waves. And they spent time together. Kip will tell you all about that.
Yeah.
So anyway, the sad part is that when it came to defending what he had as a measurement, he didn't do it in a way that most scientists would do. He said, you didn't do it my way. And that is not a way. He didn't discuss the sensitivities. He didn't discuss how he measured his sensitivity. Eventually all of that was done, but he didn't actually talk about, well, let's compare the notes. How did you do it? How did I do it? He just said, you didn't do it my way.
Yeah. So it wasn't collaborative. And
it was never collaborative, and it was quite hostile. But I can't say Richard Garwin was friendly either. I mean, he might not have been, but he look, you take a guy like Richard Garwin and you pay attention to him. He's no dummy. I mean,
right.
Anyway, what happened is I noticed the following, and I got very interested in what might be troubling him. After I taught a general relativity course at MIT, the students got fascinated by this is before he published. They were very interested how you could measure gravitational waves. And I knew only about the Weber bar. And in that course, I invented the idea of free masses. That's a separate story. But and other people had thought of it too. It's just that's the better way of doing it. But what happened is I had an undergraduate who was interested in it, and I said, look, why don't we find out? Maybe this guy's measuring magnetic pulses. And so I built a little coil, a little coil, and with electronics to store signal, to store the pulses that might be measurable. Magnetic coil, multiple turn coil, about the size of an armchair. Okay, had one in my house in Newton, Massachusetts, another one at the lab in MIT, and another one out in Chicago where Weber had his other detector. And we saw typically 2 or 3 pulses a day that was simultaneous. And what were they? They were 10 to the minus 3 Gauss, lasting for about 10 to the minus 3 seconds. Okay, what the hell was that? And I went with that on one of those visits to Weber during the Kobe days. I gave him our list of when we thought we'd seen things, and he was totally disinterested. And what he effectively said, do you think I'm so stupid not to think of magnetic fields?
Oh, so he was oppositional, and he was and that
defensive. That was enough for me to say, well, look, here's this thing that you don't know yourself what it is. You at least. Have you actually measured the magnet? I mean, it was insulting to him that somebody would come along with that.
It was like beneath him, right? And I wonder, with scientific collaborations, many of them are very fraught. There's oftentimes, clamoring for credit, for recognition, sometimes for prizes. They were a study done by a historian of science, like how many collaborations stay together after the Nobel Prize is awarded to one or two of them, and most of them dissipate for one reason or another. I have heard from some of my listeners that they felt they should have been included in the Nobel Prize in 2017. I won't get into that necessarily with you, but I want to know, more generally speaking, how was it? Obviously it was important, but how difficult was it to construct what, Doris Kearns Goodwin would call a team of rivals, with Caltech on one side of the country and MIT on the other? And you guys are kind of rivals in a certain sense. You compete for students, you compete for.
I'll tell you what the real problem was. It was a problem. Look, there's no denying it. And in this book that Chip and all of the group of us are trying to write, we're trying to deal with that.
Oh, good.
Because it's not trivial. It turns out to be extremely difficult. What was really the problem, and now it comes down to one real problem. It has less to do with rivalry. That, I think, is the wrong word. It has to do with style of doing. Okay. And I blame Ron, not so much me. I can be tough to deal with also, but it was a different problem. The problem was that Ron, very clever guy, let's say exactly a lot of the ideas that made our detection possible, several of them are due to Ron, but not exclusively due to Ron. For example, one of the most important ones called power recycling was also invented by one of the German scientists who was at the Garching Institute, who had started working on this as well. One of the ideas, the other very important idea, I think the one that he's singularly responsible for, is how to lock a laser to a cavity. In other words, you have a Fabry-Pro cavity. How do you do it? And many of us did not think of this. The guy who had thought of it first was Bob Pound, the same guy who did the Mossbauer experiment.
Mossbauer, yeah.
Yeah, but he did it during the time when he was in Rad Lab. I don't know. Have you ever worked with a klystron in your life?
Yes. Yeah. I mean, I got a good sunburn from it once. Yes.
Klystron, really. Well, they're miserable devices.
They're different.
They're more miserable. I don't know if they're more miserable than magnetrons, but they're pretty miserable. And what Bob Pound did is, during the war, Second World War, he invented a very clever technique for locking a klystron to a microwave cavity. And that idea was then repeated by Drever in an optical setting, and it worked beautifully. And so I want to give the credit to both Pound, but mostly to Dron, for thinking about that. And that now is a tool that is used by everybody in everything that involves lasers and getting single frequencies.
Right.
It's called Pound-Drever-Hall locking. Okay. So look, I don't want to take away from Ron anything. It's just that here, the problem you do have to realize is that he was a child. That's the problem. And it's even it goes back to things that must have been true when he was a young kid. The transition he couldn't make is a transition that a lot of people can't make. And that is from tabletop physics, where you are making all the decisions with your graduate students. And he barely listened to his graduate students, and he never listened to his own postdocs. I mean, he would order what to be done. That was a very unfortunate part of the way he operated. So he never got the benefit, the best use out of the people who worked with him. Okay, and that will be in that. Unfortunately, that'll be in our history. But here comes the real problem. Why did we get into trouble? We got into trouble because I was ambitious about, which had to do with MIT more than Caltech. I was ambitious because of the way MIT was looking at the whole field of gravitational wave physics. At that time, when I started, MIT wanted no part of it. And I couldn't put graduate students on the prototype. Why? Because it was an engineering fight.
Right, yeah.
And there wasn't going to be any science coming out of it. And I was told that many, many times. And so they weren't going to risk a graduate student's life on a thing which didn't look to them like it would be worth the trouble. So, and there was nobody at MIT who believed in black holes at the time. Phil Morrison, who was probably, you may not know, but maybe you do.
Yeah, I know.
Phil was dead against, I mean, he would invent the most incredible schemes to make it so you didn't have to invoke a black hole for what the X-ray astronomers were seeing. So consequently, there was no sympathy for black holes at MIT at all. So they felt the technology was too hard, and also there were no sources anyway. The hell with them. And so I was in a very complicated situation, and what came of it is that I felt the only way I could stay in business at MIT in this business is to immediately start pushing for a Ligo, a full-scale thing, because I could prove on paper, I had proved, you could not do it with a small device. Okay? So there was a mindset that was already different between Ron and myself. That was when Ron got into this thing, which was some number of years later, I already, because of the experience with having to prove that there was science in this, I had made this next step. Even though not everything was working yet, I said, look, if I'm going to work on this thing, it's got to be on a scale.
It has to be scaled up. It
has to be scaled up, and we're going to have new problems when we do that. We got to find out what those problems are.
Did they think the 40 meter at Caltech could detect to do any science?
Yeah, well, that's what Ron's in his secret little head. He kept thinking he's going to do an end run around all of this. Okay, yeah. And so that's absolutely true. That's what was going on in his head. So what happened is, here's the tragedy. This is where the tragedy happens. It happened that I had made the transition from tabletop to bigger physics, and Ron had not. And he could, and there's a difference in style when you make that. The style is a small group, and you were running it yourself. There's not that much money involved yet. Well, you know yourself. You've been through this.
Yeah, of course.
And then when you go to something big, you have groups, you have subsystems, you have organization. And that's where the thing fell apart.
It reminded me of, sort of like Apple Computer or something like that. They start off and they're in their garage, and then there are those that say we can change the world. I just need to build a bigger garage, basically. And then there was those that think, it's just, this is what got us here. And so we have to keep this spirit alive. And you see a lot of companies, go out of business. I always say that entrepreneurs and experimental physicists have a lot in common. I mean, we both have budgets to manage. We have people to manage. We have travel. We don't make any profit. In fact, we lose money on every sale. But
I don't disagree with you. Yeah, but the motivation is different.
But how did you personally deal with that? So I have to say I paint a little bit more of a sympathetic. I didn't know him at all. I never met him when I was at Caltech. But I make the point in my book in Losing the Nobel Prize here. I'm going to send you a copy because I don't know if I gave you one. But the point that I make in the book is you guys made the announcement in, say, February 10th of 2016. And that was 10 days after the nomination deadline had closed for Nobel Prize nominations, of which I was one of the nominators that year for the 2016 Nobel Prize. And I kept waiting because I had heard this rumor from Lawrence Krauss that there was big news coming out of LIGO. And I remember I gave a colloquium there in September at MIT.
September of what?
September 2015, right when you guys were analyzing.
Well, that was a day it happened. Careful.
No, it was September 20th. It was like a week or two afterwards.
Okay, I'll tell you that one. Okay, that's important that you get that one right.
Yeah.
Okay. So let me tell you.
Yeah.
We didn't know what the hell we had. Okay.
He says you did. Krauss says you did.
No, well, what the hell does he know? He's a theorist. I know Larry, and he was sniffing around. He heard because of the collaboration, and there were people, I don't know where he got it from, the people at Arizona. I don't know who gave him this bad piece of information, but we didn't know what we had. Okay, and let me give you some of the drama that went on between the 14th of September 2015.
And Boxing Day.
February, whenever the hell we published it, the 3rd, 10th, whatever, I'd forgotten. Tufts 2016. That was hell debate going on inside of LIGO. I mean, we thought, the very first thought was, I don't know, you know this story or not?
I don't know. I probably know it, but my audience may not. So please share it.
Okay. Well, I mean, the thing is that we thought the very first thing was we had already done putting blind injections into the data. That's famous story.
Yeah.
And turns out that the very first, everybody went around sniffing around. The people who were going to make the blind injections hadn't even written the software yet. Okay, so that was out, but it took a day to find that out. But that didn't end it. That was easy. The next one was how do we know we weren't hacked?
Hackers, yeah.
And that took a long time, because what happened all during that time. I remember we were living with the pall of Weber in our heads.
Yeah, and Bicep 2, right? I mean,
Bicep 2. Bicep 2 is a different story.
I know it's an announcement of gravitational wave detection.
Well, look, I the day that happened, I went and talked to, who's the guy from JPL who was on the Bicep team who makes
Jamie Bach. Jamie Bach.
I said, Jamie, why did you do this? We remember in our committee we said you need more channels. You can't do it with, and then I remember Andy saying to me, look, we ought to at least find out what's there. That's fine. That's what the idea was.
Yeah.
But then to publish, that was a piece of bad judgment, I thought.
Yeah.
And I mean, no, I don't want to dump on you guys.
Look, I dump on myself in the book. I quote Andrew. Andrew used to say, the first thing we'll do is discover if there's any there, and then we'll follow it up. And we did everything except for follow it up. But you're right. You were saying that really wasn't affecting a shadow the way Weber did 30 years earlier. No,
very different. The Weber thing had gone to the point where people were writing books about it being pathological science. Okay. And in fact, Garwin was responsible in part for that, because that's a whole story internal to LIGO from 1986. I mean, when Garwin saw that LIGO was becoming something that they were even contemplating in the NSF, we'll get back to the story in a minute, but Garwin sent a letter to the head of the physics division, who he knew for other reasons, and said, look, if you're going to continue in this idea, and it wasn't written in a nasty way, but it was written with, if you're going to continue with something that could embarrass the NSF like this, okay, that's the tone of the thing. You ought to have a summer study of this. And we got a summer study together. I did it personally. So they forced a summer study on us, and they gave us very good review. But now the thing is that Garwin thought that the whole idea of gravitational waves was something that was colored by the arguments that he had with Weber. Okay. And we lived with that. And so that's why we were being especially careful. And so let's go back to the hacker hypothesis. The hacker hypothesis took us almost 4 or 5 weeks to get rid of it.
Really?
And we had a very good man within the LIGO, Matt Evans, who's now associate professor at MIT, who took it on. He made a team out of looking at, did the hacker get into the software? Did the hacker get into the tapes that recorded the data? Did the hackers get into the hardware? Did the hackers get into the photo detectors? Did they get into the laser? I mean, in other words, wow, how did they do it? And
Right.
at the time, and they kept studying and this and looking. We even locked up all the instruments. You couldn't open the chassis because we had tape on them because we didn't want anybody to mess with it. So it was one tremendous thing. And eventually, they never could prove. We could never prove there was no hacker. But the hackers had gotten so smart that they knew so much that it became very implausible.
Right.
And so, but that isn't the end of it. It turns out it looked like we could not rule out that, but it looked implausible. It looked easier to say nature did it. And then for many of us, and you can ask Barry this also, or maybe you did, what was the thing that finally triggered it that you were willing to go forward?
And
it was the Christmas, the day after Christmas event.
Boxing Day event.
That's right.
That's right. Yeah, he said that as well. And, you know, I question what would have been the history of science. What would it have looked like if that event didn't occur in this galaxy far, far away? And then he said it was all, but, you know,
it would have been, you know, a couple of months later. That's all. I mean,
and then you had the binary neutron star.
Well, that's 2 years later. That's a whole other.
I mean, that must have been a whole other level of kind of confirmation. I mean, you must know there are people in Europe, at least, and maybe in the US who claim that there are challenges still with the interpretation. You know, you're always
I know
finding the same. And I want to, you know, because I know you don't have, you know, the too much more time, but I do want to ask you, you know, specifically about, you know, some things I did talk to Barry about that involve maybe the future of this type of science. And that involves, you know, the question of which is more scientifically interesting to you. Well, let me first ask you a question. I've asked this of people like Shelley Glashow and Frank Wilczek and others, and Roger Penrose, that we talk about black holes as if they're real. And we sort of know that they're real, but the fact that we know that they're real, and you are one of the main people on Earth that's responsible for the actual visceral feeling of reality that they connote. But how do we know that we can take the leap from there to saying that they have a singularity at their core? And I've pressed this with Roger Penrose, and I haven't gotten a satisfactory response from anybody. And maybe you will provide the first satisfactory answer.
You won't get it from me. I'll tell you what, the way we established it was a black hole. It was only from two things. It was from the fact that the Kerr solution, you know what the Kerr is, the guy who did a rotating black hole. Yeah. That the Kerr solution, which is nothing more really than adding angular momentum, it's just more mathematics. It's another model for a black hole. That predicted, and be careful, there's one step further. If it hadn't been for numerical relativity, I don't know if people told you that, but if it hadn't, and Kip will certainly emphasize this when you talk to him, if it hadn't been for numerical relativity, most of the people would not have been, they would be queasy about it, because the last splash, the last, let's say, few oscillations of that waveform, where this velocity is close to half the velocity of light, the relative velocity of 0.6 the velocity of light, none of the post-Newtonian expansions that you can make of relativity. You can do that. You can do it in orders of power of V over C. You can do a metric expansion in powers of V over C. And you have to go to some incredible order, 11th order or something like that. And, you know, I don't know if you've ever done these goddamn things. Everybody who does them, you make a sign error and the whole thing blows up on you. It's no good. I mean, it's just endless paper.
I remember walking around Caltech and the halls of West Bridge and hearing Sterl Finney's office, and he would visualize the chirp and he'd go, whoop, whoop, whoop. And it was just like all day long. I thought I go crazy listening to that all day.
No, but that's okay. The chirp is not the least. It's getting it right to the end point.
Yes.
And the thing is, the chirp comes straight out of Newtonian physics. I mean, you don't have to do much with a little bit of the quadrupole formula. So you can get the first part of the thing very beautifully. But you're asking how much of the black hole's mystique do we know?
Of its essence.
And the essence of the black hole. And you will really know the black hole being different than a neutron star only from two things. And I think we're close to it, if not already proved it. There is the solution, the dynamics, the Kerr solution dynamics, gives you the waveform we see, and you can compare the waveform we have with a numerical relativity waveform that is now good to arbitrary up to, well, not, I don't know if it's good at exactly C, but it's goddamn close to it, okay? And the two match. they match. I mean, they match to as the signal to noise in the measurement. So that's very,
that gives
very
you
important.
the confidence that the
Well,
essence
that's
of
part of what gives you the confidence. But what's even more important, that came after the paper was written. Two things have happened. That paper was that we've also now begun to see the normal mode oscillations of the metric around the black hole. In other words, when the two black holes come together and they form, things quiet down, but there is still oscillations going on in the geometry.
Of course. Yeah.
Okay. And they're going on and they have normal modes. It turned out they're quite heavily damped by gravitational radiation. Those have begun to speak. We can begin to smell at them.
And that is distinct from, say, a compact object of
That's
another.
distinct from a neutron star.
Okay.
Okay. Now, what it tells you about the singularity inside the black hole, I don't know. I just don't know enough theory.
Or that it has an event horizon, I mean, the Event Horizon Telescope, I'm trying to get Shep Dolman on the podcast, but I've had on other people. And, what we're really seeing in that mystical image that we saw over a year ago now, it's almost 2 years ago, is the light shadow, it's not
you're seeing
actually
more than that. No, you're seeing two things.
Okay.
You're seeing the light shadow
The spin.
is one.
Yeah.
That's one of the things you're seeing. But the light shadow is the black part.
Yeah.
But you're also seeing something else. You're seeing the photon ring. That's a ring that forms outside. As we're going away from the black hole, we're going out from the black hole toward us. So the first thing you see that's closest into the hole is the dark part. Okay.
Yes.
Now that can be seen better if Shep had more detectors. And that's what he's doing right now.
They're working on that now. Yeah.
Because they had to do a lot of modeling to get that, you see. Okay. And he knows exactly what has to be done. Then the bright part, that ring you saw, is something which is a very different thing. That's quite far away from the event horizon, but that's the next event in that picture. And what is that? These are photons that have come in with close enough to R equal to the event horizon, but not yet at R, the event horizon. And they get captured in a ring. And what happens is they collide with each other, the photons in that ring. There's perturbations of that ring. Effectively, they come about because of, and then they sometimes leave the ring, and that's what you're seeing.
Yes, the trajectories.
So it's a photon ring, but you haven't seen the event horizon.
Right.
You're not going to see that.
Yeah.
So
nor will you see the singularity. And here's what I often hear.
You won't see the singularity. You will never see. There's only one singularity in that damn black hole. It's not the event horizon.
No,
see,
I know. Yeah.
It's the thing that's deep inside of it that tears everything apart.
Right. Well, here's my
my
my what do you call it, fracas, or my complaint against the this notion of singularities. I feel there's a lot of circular logic. In other words, we'll hear things like we need a quantum theory of gravity because we don't know how to explain the properties of matter and energy and gravitational fields at small distances and high energy. In other words, we don't understand it. And where do we find two scenarios where fundamentally gravity seems to need a quantum analog to it, like a graviton description? And that is at the singularity of a black hole and possibly at the singularity at the Big Bang. And
you guys are going to find it.
That's the thing. So this is what I want to ask you. But
wait a minute. That's very important. That to me is the next most important thing that's going to happen in this field. Now, whether B modes do it, and I hope they do. I hope you can get around all the foregrounds. And I don't know if R of 0.001 will do it. I know that's about what you can do.
That's
at least
about it.
What I've heard. I hope it can do it. But that's not the end of the story. I think if you see something or if you don't see something, the next generation of people who go into the business, into gravitational wave detection, will push like hell for something that can do it, that can actually measure it.
Okay, so
that will be called, I don't know if you know this, it's called Big Bang Observer.
I talked to Barry a little bit about the future plans for it. Yeah. But I guess I still haven't made the final point, which is that even if we see B modes, we're not seeing gravitons. We're seeing the classical analog. And I want to add, and certainly we'll never see the singularity in a black hole. So my question is, what if there is no Big Bang? My friend Paul Steinhardt, my friend and your fellow laureate now, Sir Roger Penrose, they have very bright minds. They have super brains, right? And they don't believe there was a singularity at all. In fact, they believe evolution is purely classical. And so my question is there a generation of young theorists that are perhaps wasting their time because they're pursuing something which can never be seen in the case of a singularity at the core of a black hole, or may not exist in the case of a singularity at the origin of time? So
Well,
are we
I'll tell you,
wasting
I mean, you're asking a hard question for a person. I'm not a theorist, but my prejudice is that it would be quite amazing, given all the analogies between electricity and magnetism and analogies. They're not perfect analogies, and I can give you many examples where the analogies break down. But there is enough there that I think it would be a miracle to me if there wasn't a quantum theory of gravity.
Interesting.
There's got to be. I mean, why should that be left out? And the thing is that, not that we have seen it, and many people say, well, can't you do that by looking at the granularity of the waveforms you're looking at? Well, I wish we could, but you know, you're dealing with the number of gravitons in there is, you know, in the 10 to the 30 department, you know, that kind of thing. So it's not, and looking for what you're asking about, looking for some evidence of the singularity in the black hole that you can see from the outside of the black hole is probably iffy. One place where I think you might be able to do something is from the spectrum of the spectrum of the gravitational radiation that you may not see in B modes because you're going to see an integral.
Yeah.
But that you could do if you actually looked over a few frequency bands.
Yeah. So if you had like the Big Bang Observer plus the CMB and you both detect it, you'll get what's called the tensor spectral index. And that would be, at least some more circumstantial, if not convincing evidence.
Well, I'll tell you, I mean, the fact is that you'll love this story, is that during the Kobe days, I would occasionally, I go from MIT to Goddard a lot. And on one occasion, Alan Guth wanted to go to give a talk at Goddard about, where Kobe was going. And he wanted to give the people on Kobe a little pep talk about what this new idea. And so I'm driving on that road on the highway to Washington from the Baltimore airport. And we'd been talking. And I finally asked him, don't you think there might be gravitational waves that come from inflation? And he didn't say anything for a while. And what we knew at that time, a lot of people had guessed that, including Steve Weinberg, that maybe there would be a 1 degree Kelvin background of gravitational waves, which of a Planckian variety, which is absolutely hopeless to detect. Yeah. Okay. And when we got to the gates at Goddard, and he said to me, probably not. And there probably are none. And so here's Starobinsky's papers on what might have happened. And the difference between Allen and Starobinsky is Allen he had particles that did it, but he did the calculation classically. Starobinsky did it as particles, but quantum mechanically. And to him, the big thing that caused the gravitational waves were the fluctuations.
Interesting.
The quantum fluctuations are what caused the gravity waves. And that's a spectrum that anybody who's working in that field now uses there are other points less well defined, like, for example, phase transitions from different epochs. Right. That's certainly there. But the thing is that if it's there, but the one that actually has to do with inflation has to do with the quantum theory. And if Starobinsky's right, that's the only way I think you're going to get any evidence for the graviton.
Interesting.
Okay.
So there'd be the spectral kind of encrypting very interesting. Yeah. I want to turn to a couple of questions from my friends and your friends that are at MIT. So one comes from Professor Max Tegmark. He asked me to ask you, why did your dean draw a huge 0 on a piece of paper decades ago?
Well, I think I told you that in about half an hour ago.
Yeah, okay. That's the lack of backing that I think was not Kip and Barry and Ron didn't have to contend with it. I mean, Caltech has had a long history. Oh, yeah. Mainly thanks to Kip, right?
Well, it's more than that. I mean, I give Kip and Caltech credit for the fact that the whole field didn't go under.
Yeah.
Okay.
Yeah.
I mean, and I in that book we're writing, I have, if my sentence stays in the book, it was a watershed for the field that Caltech went into this.
Did you ever think of leaving MIT?
It's hard when you have, how old are your kids?
I've got 5 of them and nine down to 2. So
Well, they're not old enough yet.
They're not old enough.
You could still move.
Is that an offer? Are you propositioning me, Ray?
No, I'm not propositioning you.
I'm very happy here. I would also have to deal with a death sentence from my wife.
No, what I'm talking about is that once you have an interest in boyfriends and girlfriends, and you have become part of the society, and that means you become an adolescent. It's very hard to move kids.
No, I know, and I love it here. It's phenomenal. But I love MIT. MIT is a wonderful institution.
I'll tell you one cute story about that. One of my colleagues, David Shoemaker, and I had gotten quite desperate about this. And David is one of the older gentlemen in the field now. And we had thought, this is we had made an offer indirectly by Stanford. And it wasn't whether we didn't know if it was Stanford or Stanford Accelerator that was making the offer, that to take the whole laboratory, our laboratory, they knew about problems. That was not a mystery to anybody.
Right.
At Stanford. And so what happened is he and I went out there to try to sniff it out, see if there was anything. It looked pretty good. They wanted to build the Ligo next to the accelerator. They wanted to have.
And they're working on GPB, right?
But that's part of the story. So anyway, we're getting to the down to it. Joe Taylor was in particular one of the guys who was very anxious to see gravitational waves at Caltech. So I went to speak with the head of the department, who was then later became head of Department of Energy, Steve Chu.
Steve Chu, yeah.
And I go in his office, and he looks me square in the face, and he says, "Look," "we've got one crazy experiment. We don't need two." That ended it.
Yeah, I talked to Clifford Will about this not too long ago. And yeah, he was on some of the review committees for this 50-year-long experiment, which some say was a huge boondoggle. But somehow they kept getting funded and funding.
No, I tell you, I have a different view. They measured it.
They do, yeah. Oh, I think they did, but how long did it take? How many careers did it take? How much money did it take? And what did it do to Stanford? I mean, it was a huge, albatross, according to many of my friends. I was a postdoc there during the late 90s, and a lot of people felt a lot.
Who were you with? You with Church?
I was with Sarah Church, yeah. And before she fired me. But that's a story for another time. I want to end with one other question before I get to the question I ask all my guests that are honoring me by your presence. And this is from David Kaiser, who is a professor alongside.
I know him. Of course I know him.
So we talked about how it was to kind of work on projects when it was sort of considered to be almost like fringe. And I wonder, you're kind of different, because it was like, I don't know if you know this guy, Michael Jordan, the basketball player, right? So
no, I know the name, but I don't know what he does.
Yeah, he was like considered the best basketball player in history. Yeah. And then he quit and retired at the top of his game. And then he went off and he tried to play baseball. And it kind of reminds me of, my friend Jim Simons, who's sponsoring the Simons Observatory. Yeah. His kick lately is that he should win the Nobel Prize for this Chern-Simons.
Yeah, I know.
Yeah. So, I'm thinking, Jim is worth, he's an MIT grad. He's worth billions.
I didn't realize he went to MIT.
Yeah, he was an undergrad at MIT. I think he worked with Singer, and he was in the math department.
Oh, so he worked with a cosmology guy. Singer, Singer's a complicated man. Siegel is the complicated. Siegel is the cosmologist. Oh, Siegel, that's right. Siegel, you're right.
He worked with Singer. But anyway, they're both interesting guys. Yeah. And I think you had Kobe, which eventually garnered 2 Nobel Prizes, and then you had Ligo, and for so long, I made the point to Barry. I think for Barry's career, the cancellation of the super collider was like the best thing that could have ever happened to him, because he went on to go and work on Ligo after that. And if he had stayed with the super collider, and if it had succeeded, he wouldn't have won the Nobel Prize, because that went to none of the experimentalists on the LHC, right? So I said jokingly, and he's like, I don't play those games. But with you already had Kobe. I mean, you made this phenomenal impact on so many people, on the discovery of something so foundational, and yet you still kept working on this project that many people consider to be fringe. So what gives you that courage? Is that just the way that you were born, or I mean, is there some tangible lesson that we can learn from your experience of having super successful thing and then a moonshot that could be a big waste of time and money?
Well, I never think that way. See, that's the trouble. I don't think the way you're talking.
Mm-hmm.
And let me tell you that the Nobel Prize, or where this particular experiment ends, whether it's successful or not, isn't the thing that is in my mind. What's in my mind, is it interesting? That's the first question. Am I going to do something which isn't interesting to me or even anybody else?
Mm-hmm.
And the another one, which is much more pedestrian, is it fun? Okay. And I found both of those things kind of fun and important. And they started in my lab at about the same time.
And you told me over dinner, we had dinner with Alan Guth and the late great Andy Friedman, who passed away sadly this year, and Max Tegmark. And you said, at any given time, there are only 4 or 5 people who fully understand LIGO from soup to nuts. And, I wonder, can experiments get too big? I don't think there's anybody who understands like every aspect of the LHC or maybe even of the Simons Observatory that I'm working on. Can an experiment get so big that it loses that interest and fun factor that made LIGO appeal to you so much?
Well, be careful with that. There's a difference between LIGO and high energy physics still. It's not quite, you are not yet regimented completely. And that's something my colleague who made trouble, this is Drever, never really understood. There was still within LIGO so many things that used your imagination and made you feel that, yes, you had a job to do. And if it succeeded, you would have another interesting thing to work on. And so you still felt within a constrained that you couldn't take crazy things on anymore, but that you were functioning in something which was very important. And what you were working on was fun. I'll give you many examples. For example, for a while we were screwed by Barkhausen noise. That's something I worked on. Why? Because it was making noise in the magnets and that pushed the masses around. So I did a whole experiment on that, and I came up. Yeah, it turned out it was a problem. That was fun to work on. In the beginning, we had done something completely idiotic. We bought a lot of switching power supplies. Stay away from switching power supplies if you're doing anything delicate. That's right. And they were just, you couldn't even walk near the place without getting a note from the FCC saying you guys are a radiation hazard. A radio. So anyway, there were many, many puzzles like endless puzzles that came up, and I got mixed up. I'll tell you something very pedestrian. The vacuum tube, the vacuum of the vacuum tube, of the big long tube. In fact, that became very important in my life for about 4 years. So it turns out everything I touched, there were people who I enjoyed working with, and they were things that didn't regiment. You were still not yet in a regime where you couldn't see what was going on otherwise.
It was always.
And I think there are people in LIGO who know enough about everything part of it that they can say, yeah, if there's a problem, it's probably in this subsystem.
Interesting. So that was kind of micro projects that add up to the success of the whole project, and each micro project is fun in and of itself. I think that's wonderful. So I want to ask you a couple of questions before we conclude, and these are questions that I ask guests who all honor me on their by coming on my show, and it really harkens to essentially aspects that are important to me of life outside of physics, because I think in the conclusion of my book, I lusted after the Nobel Prize until I went through this episode where I came close to, possibly being involved with a project for it. And I came to see it as, a byproduct. Over my shoulder over here, you can see Maria Gephardt-Mayer, who won the Nobel Prize. And she has a quote, you can't see it, but it says, winning the Nobel Prize was only half as much fun as doing the work. And I didn't realize that.
That's good. Good. I'm glad you have that there.
Yeah. So I keep that in, and that's actually on a poster. I have 2 daughters, and I put her poster up in each one of their rooms. And the other day, my older daughter, who's 4, she said, "Dada, is Maria still alive?" And I said, "No, she's not alive." And then my daughter, she says, "Did she die? Did she?" Yeah. So I said, "Yeah, she died, but she made wonderful contributions." Okay, these are things that involve death, unfortunately, but I'm not going to get too gruesome here, Ray. But it is the anniversary of Alfred Nobel's death. He did die 124 years ago in 1896 on this very day that we are speaking, December 10th. And that's why they give the Nobel Prizes out on this day. Typically, although this year they didn't do it because Stockholm is locked down, right? Because of COVID. Yeah. So Alfred Nobel had a will, and it said that the prize should go to the person who made the greatest discovery or invention and conferred the greatest benefit to mankind. And as you know, Alfred had no wife, he had no kids, he had no heirs in that way. So he left basically all of his money to the prize. Plus, he endowed what we call in Hebrew an ethical will, a zava'ah. It means a wisdom will. What do you want to leave to your heirs in terms of wisdom that you've accumulated in your 88 years on Earth? And may it live to the biblical age of Moses, 120, Ray. We need you, Ray. But I want to ask you, what kind of piece of wisdom would you leave to future generations that you've accumulated?
Well, you're going to be very upset with me. Okay, I can tell you that already. And it's the advice that I give everybody, but I give it to myself also. If it isn't fun, get the hell out of it.
That's great. Okay. That is perfect. Thank you, Ray. Okay. Next one is a question I ask. You've seen the movie 2001, A Space Odyssey with...
No, I don't know it, no.
Well, there's a scene in it. We can skip over part of it. I do want to note that there was a Voyager satellite that Carl Sagan, here's a puppet of Carl Sagan. Someday we'll get a puppet of you, Ray. I have a puppet of Noam Chomsky, your neighbor down the hall.
Good for him.
But I'll get a puppet of you someday.
He's still alive, right? Noam he isn't dead yet.
No, he was on my show earlier this year. Actually, I think he's younger than you. Yeah. I think he was born. No, he's the same age. He was born in 1932 on December 7th. So he just turned 88 or 80.
So he's a little younger than I am. Maybe a couple of months.
Couple of months. Yeah, exactly. So there's a plaque affixed, a golden disc affixed with a phonograph needle can play it that they put. Carl Sagan convinced NASA to put this record on the Voyager satellite that contained sounds of planet Earth. And it was meant, I actually talked to Carl Sagan's widow, Ann Drury, and she runs this Cosmos program on TV and has written books. And she actually had her brainwaves recorded and transcribed onto this phonographic disc, which appeals to your past upbringing and your experiments that we talked about at the very beginning of this podcast. But this disc is meant to last for 1 billion years. And it's sort of a time capsule that will go out into infinity, so to speak. Hopefully it'll be discovered, and on it is inscribed all these wonderful things. I want to know, if you had your own billion-year time capsule, what would you put on it? You know, Richard Feynman said this as a famous cataclysm, destroyed all of scientific knowledge were to be destroyed. And only one sentence was passed on to the next generation of creatures. What sentence would I, Richard Feynman, make that contains the most information in the fewest words? I believe it is the atomic hypothesis, that all things are made of atoms, little particles that move around. I want to ask you, scientific or otherwise, what would you like to put on a time capsule that would last 1 billion years?
Well, that's a hard one. Boy, I haven't thought about that. But I think the most important thing is look around and see if you can draw conclusions. That would be I don't think I can tell you anything better than that.
Yeah. It's kind of the experimentalist perspective. Right. Yeah. Drawing inferences from what surrounds us in nature. Last question, and then I'll let you go. You've been so generous with your time. I want to go, instead of going forwards in time to your ethical will and your billion-year-old time capsule, I want to go backwards in time. So I don't know if you know Sir Arthur C. Clarke or what he said, but he said a couple of famous things. He said, any sufficiently advanced technology is indistinguishable from magic. He said, for every expert, there's an equal and opposite expert. I like that one. At the faculty lounge, I like to use that phrase. And then he said, the only way of discovering the limits of the possible is to venture a little way past them into the impossible. And that's the name of this podcast. We're named after this phrase. I want to know, what advice would you give to a 20-year-old Ray Weiss from an 88-year-old Ray Weiss? Advice to your former self that seemed impossible back when you were a youth, but now seems eminently doable because of your courage or insight or just sheer drive.
Well, that one's easy. At least for...
I can leave you with an easy one. For us, you'll come back when your book is out.
No. What you do is, once you've learned a little bit, you can't just... And this is one of the problems that I think a lot of the kids have today, that it doesn't take some investment to do what I'm about to say, okay? That you can... And this, I think, has happened because of the barrage of information that comes from everywhere. But... you just don't make anything up that is of very much value until you've been around to think a little bit about it. That's one of the things. But the thing I would say is make sure that you keep looking at the fresh ideas that occur to you. because some of them might actually be interesting. Okay. And don't just say it's too hard or that it's, if you think there's something there, well, it's worth your time. And I can say this with what's happened to me over and over again. I mean, some of you start in a new field. And that's another thing. I don't know. You don't always stay in the same. I don't know what you did, but I'd say to most people, look, if you don't every 5 years, especially as you're young, you get your PhD in field X. And if 5 years later, if you're still doing field X, you haven't asked yourself enough questions. But you should at least ask yourself the question, am I getting what I like out of this? Mm-hmm. Is it still fun? Is it still interesting? And then you might just jump into something else. That's not the reason I went into gravitational waves. That was there all the while. But that's a questioning of, is what you're doing interesting still to you? Or has it become a habit? Is something you've got to figure out for.
And are you learning something new?
Yeah. Is there something new that occurred to you? And boy, it's worth thinking about that.
It is.
Your mind is remarkable. I don't know how it gets stuff. But, it's amazing what comes out of it.
Yeah, so, it's amazing. This computer made of fat, can do so much stuff.
Well, it almost makes you religious. You got to be careful.
Yeah,
Let me ask
exactly.
you a question. You were going to tell me something. Now, here you are, Keating, which is a nice WASP name.
That's right, Irish Catholic.
And you're a good Jewish boy from New York.
I am.
Tell me what happened.
Okay, well, I'm going to send you a copy of my book so you can read it. But the short story is, both my parents are Jewish. They're born biologically Jewish. And I was raised maybe once a year on Christmas. We would go to synagogue, maybe, or Chinese food. That was about the extent of our Judaism. Then my parents got divorced, and my mother married an Irish Catholic man with 9 brothers and sisters named Keating. So I changed my name from Axe to Keating when my stepfather adopted me when I was 7 years old. And then, to make things even more complicated for you, I became an altar boy in the Catholic Church at age 13, which you'll recognize as the age when Jewish boys are supposed to have their bar mitzvah.
Exactly. Yeah.
Never had a bar mitzvah. I was an altar boy in the Catholic Church, and I loved it. And then I went to college, became an atheist. And then after 9/11, I started to realize this country of Israel seems to be important. It seems to be involved in a lot of affairs on planet Earth. And I knew nothing about it. I knew more about Christianity and atheism than I knew about the religion of my birth. And I was kind of stupid because I said, well, Christianity came along after Judaism. Jesus was Jewish. We know that. And so they must have, like, anything that was wrong with Judaism, Jesus and the further Christians must have kind of tweaked that and made it agree with data or empirical evidence or whatever. And so if I can rule out Christianity as being like, I don't believe in this transubstantiation or a resurrection, then I can disprove, modus ponens, I can disprove Judaism. So that's what I did. And so I was an atheist for a long time until I started to get serious about wanting to have a family and get married and learn about this vast, wonderful history that I felt had been kind of denied and literature and so forth. So now I study Talmud, I read the Torah. I actually know more, at least I can read Hebrew now. And I do want to wish listeners a happy Hanukkah, because tonight is the first night of Hanukkah. And I thank you for that question. I'm going to send you a copy of this book, so I'll email you for your address, Ray. And I would love it if you gave it a read. Barry read it, he enjoyed it, and he wants to talk more about it as well. So hopefully I'll have you and Barry and Kip, and then I'll have you all back when you guys come out with your book next year. God willing, we'll have a better 2021 than 2020. I want to thank you so much, Ray.
Okay. Well, thank you for this. You're a good interviewer. Okay. You did well.
Thank you so much. I hope we'll talk again. We'll Zoom again. Bye,
all
Ray.
Right.
Any sufficiently advanced technology is indistinguishable from magic.